Hello, we are César, Farrera and Brian Durán, and together we will review Chapter 3, Network Protocols and Communications, in Cisco's CCNA course. In this chapter, we will review the rules of communication, network protocols and standards, and moving data in the network. But first, let's start off by defining what communication is. For communication to exist, there must be at least three elements: the message source or sender, the destination source or receiver, the channel, which is the pathway where the message travels from source to destination. There are certain rules that govern communication, for instance, common language and proper grammar. If these rules are not respected, communication between humans is not possible. Take for example the text on the screen. The same applies to computers. These rules are called protocols. Protocols help identify sender and receiver in a network, as well as how the message must be transmitted. Protocols cover several areas such as encoding, formatting and encapsulation, message size, timing, and delivery options. We will now review each one in a bit more detail. Encoding is the process of converting information into another acceptable form for its transmission. Decoding reverses the process in order to interpret information. In computer networks, the bits are encoded into special patterns of sounds, light waves, or electrical impulses depending on the type of media. Those signals are then received by another computer which decodes the signals back into bits so it can be read as information. Encapsulation is the process of placing one message format inside another. Think of it as a letter. The actual contents of it are placed within an envelope. All computer messages are encapsulated in a specific format called a frame. The frame provides the address of destination and source host. The format of the message and the frame depend on the type of media and channel. If a message is not formatted correctly, it will not be successfully delivered or processed. In communication, size matters. Protocols that rule over a message size are very strict and will not transmit a message if it's too long or too short. Long messages are broken down into smaller frames. This is known as segmenting. The receiving host de-encapsulates the messages and puts the pieces back together for it to be processed. Timing is important when sending and receiving a message, since it can help avoid errors. In networks, an access method is needed to know when to begin sending messages and how to respond when errors occur. If there is no such thing, a collision of information occurs, and it's necessary for both to resend the message. Flow control regulates the correct timing and quantity of data for successful communication. For example, if a host sends too much data, the receiver might not be able to handle it. Response timeout is the amount of time it takes for a host to assume that the receiver did not get the message. If a message reaches timeout, the sender can continue sending messages or resend the failed one. It depends on the kind of network. Finally, delivery options vary according to the message. It is important to specify the amount of receivers the message will have. It can be unicast, one-to-one, multicast, one-to-many, or broadcast, one-to-all. The difference between multicast and broadcast is that broadcast sends the message to all the hosts in the network, while multicast sends it to at least two hosts. Sometimes it is required that the receiver sends proof of receiving the message. This is known as acknowledgement. A group of protocols that are related are necessary to communicate through a network. This group is called a protocol suite. A suite defines a common format and a set of rules for exchanging information. An example of a protocol suite is the interaction between a server and a client. Many protocols work together to ensure that the messages are understood by both computers. The application protocol, such as HTTP, governs the way the server and client interact. The transport protocol, TCP, manages individual conversations between servers and clients, controls size and rate of information. Internet protocol, IP, takes the segments from TCP, encapsulates them into packets, assigns an address, and delivers them. Network access protocols allow the communication over a data link and the physical transmission of data on the network media. Protocols and suites can be an open standard, which is being freely available to the public. Examples of these are IP, HTTP, and DHCP. They can also be proprietary, which means that a company controls the definition and how it works, and to use it you must ask for a permission. A standards-based protocol is one that has been ratified or approved by a standards organization, such as the IEEE. The TCP/IP suite is used for transmitting and receiving information through the internet. It contains a lot of protocols in each of the 4 layers that we discussed before. These can be seen in the image on screen. We will now see how the TCP/IP suite works. First, the HTML is the data that the server sends to a client. The application protocol, HTTP, adds a header to the data. The HTTP application layer delivers the data to the transport layer. The TCP manages the conversation between server and client. The IP information is added to the front of the TCP information. It adds the source and the destination address. The Ethernet protocols add information to both ends of the IP packet. This is the data link frame. The data is then transported through the network. The client receives the data link frames and removes each header in the opposite order in which it was added until it reaches the HTTP information. Finally, the page information is passed on to the client's web browser.
Open standards encourage competition and innovation. They also guarantee that no single company's product can monopolize the market or have unfair advantage over its competition. The Internet Society (ISOC) facilitates the open development of standards and protocols for the technical infrastructure of the Internet, including the oversight of the Internet Architecture Board (IAB). The IAB provides oversight of the architecture for protocols and procedures used by the Internet. The IAB consists of 13 members, including the chair of Internet Engineering Task Force (IETF). One of the key responsibilities of the IETF is to produce requests for comments (RFC) documents, memorandums describing protocols, processes, and technologies for the Internet. The Internet Engineering Steering Group (IESG) is responsible for the technical management of the IETF and the Internet standards process. The Internet Research Task Force (IRTF) is focused on long-term research related to Internet and TCP/IP protocols, applications, architecture, and technologies, while the IETF focuses on short-term issues of creating standards. The IRTF consists of research groups for long-term development efforts. The Institute of Electrical and Electronics Engineers (IEEE) is a professional organization for those in electrical engineering and electronics fields who are dedicated to advancing technological innovation and creating standards. The IEEE 802 family of standards deals with local area networks and metropolitan area networks, including both wired and wireless. The IEEE 100.3 and IEEE 802.11 standards are significant IEEE standards in computer networking. The IEEE 802.3 standard defines media access control for wired Ethernet. This technology is usually for LANs, but also has wired area network applications. The 802.11 standard defines a set of standards of implementing wireless local area networks. International Organization for Standardization is the world's largest development of international standards for a wide variety of products and services. In networking, ISO is best known for its Open System Interconnection (OSI) reference model. The OSI protocol suite is implemented on telecommunications equipment. There are benefits to using a layered model to describe network protocols and operations. Using a layered model assists in protocol design because protocols that operate at a specific layer have defined information that they act upon and defined interface to the layers above and below. Fosters competitions because products from different vendors can work together. Prevents technology or capability changes in one layer from affecting other layers above and below. Provides a common language to describe networking functions and capabilities. There are two basic types of networking models. Protocol model. The TCP/IP model is a protocol model because it describes the functions that occur at each layer of protocols within the TCP/IP suite and represents the functionality required to interface the human network with the data network. Reference model. This model provides consistency within all types of network, protocols, and services by describing what has to be done at a particular layer, but not prescribing how it should be accomplished. As shown in the figure, the TCP/IP and OSI models are the primary models used when discussing networking functionality. The 7-layer OSI model has made major contributions to the development of other protocols and products for all types of new networks. It also describes the interaction of each layer with the layers directly above and below it. The TCP/IP protocol model for Internet network communications was created in the early 1970s. It defines 4 categories of functions that must occur for communication to be successful. The protocols that make up the TCP/IP protocol suite can be described in terms of the OSI reference model. At the network access layer, the TCP/IP protocol suite only describes the handoff from the internet layer to the physical network protocols. OSI layers 1 and 2 discuss the necessary procedures to access the media and the physical means to send data over a network. OSI layer 3, the network layer, is almost universally used to describe the range of processes that occur in all data networks to address and route messages through an internet network. IP is the TCP/IP suite protocol that includes the functionality described at OSI layer 3. Layer 4 describes general services and functions that provide ordered and reliable delivery of data between source and destination hosts. These functions include acknowledgement, error recovery, and sequencing. The TCP/IP application layer includes a number of protocols that provide specific functionality to a variety of end-user applications. The OSI model layer 5, 6, and 7 are used as references for application software developers and vendors to produce products that operate on networks. A single communication, such as music, video, or an email message, could be sent across the network, divided into smaller pieces. This division is called segmentation. By sending smaller individual pieces from source to destination, many different conversations can be interleaved on the network. If a particular path becomes congested with data traffic or fails, individual pieces of the message can still be directed to the destination using alternate pathways. If part of the message fails to make it to the destination, only the missing part needs to be transmitted. As application data is passed down the protocol stack on its way to be transmitted across the network media, various protocols add information to it at each level. This is commonly known as the encapsulation process. The form that a piece of data takes at any layer is called Protocol Data Unit (PDU). During encapsulation, each succeeding layer encapsulates the PDU that it receives from the layer above in accordance with the protocol being used. The PDUs are named according to the protocols of the TCP/IP suite as shown in the figure: data, segment, packet, frame, bits. The encapsulation is the process used by a receiving device to remove one or more of the protocol headers. The data is encapsulated as it moves up the stack toward end user application. To understand how communication is successful in the network, it is important to understand the roles of both the network layer addresses and the data link addresses. The network layer addresses or IP addresses indicate the network and host address of the source and destination. When the sender and the receiver of the IP packet are on the same network, the data link frame is sent directly to the receiving device on an Ethernet network. The 48-bit data link addresses are known as Ethernet MAC addresses. Most network applications rely on the logical IP address of the destination to identify the location of the communicating host. The data link MAC address is required to deliver the encapsulated IP packet inside the Ethernet frame across the network to the destination. The sending host uses a protocol called Address Resolution Protocol (ARP) to discover the MAC address of any host on the same local network. Only the device with the IP address contained in the IRP request responds with an IRP reply. It is important that the address of the default gateway be configured on each host on the local network. If no default gateway address is configured in the host TCP/IP settings, or if the wrong default gateway is specified, message addresses to hosts on remote networks cannot be delivered. If IP addresses indicate the network and device addresses of the source and destination, when the sender and receiver of the IP packet are on different networks, the Ethernet data link frame cannot be sent directly to the destination. The Ethernet frame must be sent to another device known as the router. Each device knows the IP addresses of the router through the default gateway address configured in the TCP/IP settings.